Another method which is also used called the predictor-corrector algorithm is a higher order algorithms that use the transformation or information of the higher order derivatives of the atom coordinates. So instead of taking only the DRDT, here also we use these, let's say or D2 RDT star. Essentially we use del QR, del RQ and all. Okay. So the first we do the prediction step. So we use the predictor. So the position, velocity and acceleration at time t plus delta t are predicted by the Taylor expansion using their current value. So that means if you want to get t, the position, velocity and acceleration at time t plus delta t using their position at time t, velocity at time t, acceleration at time t. Okay, so these are the kind of the prediction. Okay, prediction for position, prediction for velocity, prediction for the acceleration. So as you can see that we are using also some of the higher order differential also. Okay, now higher order differential gives you are using in the prediction case. Then what we are doing that we are calculating the error. Okay, so the force is computed at time t plus delta t, taking the gradients of the, we know the potential at any position, so we can do the differential of that potential with respect to position. We get the force. Okay, at t plus delta t, and from the force we can easily calculate the actual acceleration. Okay, so that resulting acceleration a t plus delta t from this force will be in general difference from the predicted acceleration. What is predicted acceleration is here. Okay, and this difference, so this is getting, we are get from the negative differential of force, and this is from the prediction. Okay, so this take the difference of it, so you get the error in the acceleration. Now in the second step, in the corrector step, we use this delta A or this error in measuring or estimating the acceleration. Okay, so in the corrector step, the position and velocities are corrected proportionally to the calculated errors. So corrected positions will be the predictor position plus a constant into the error in the acceleration. Okay. Similarly, the corrected velocity will be the predicted velocity plus a constant into the of course this C0 and Ci will be there. So the units will be different to make it a kind of a position and velocity. Okay, this constant Ci means C0 and C1. Of course, at different atoms we will be having this different the different C0 and C1 value at any step. Okay, depend mainly on how many derivatives are included in the Taylor expansion, and they generally vary between 1 to 0. This method is very accurate and stable with almost no fluctuation during the run, and is especially good for constant temperature molecular dynamics. However, it is not time reversal. Time reversal means whether if you just change plus delta t to minus delta t, whether it is reversible or not. Okay, or it's remaining same or not. Okay, however, it is not time reversible due to the involvement of the error correction. Okay, but the earlier methods, the Verlet methods are time reversible. The methods has a tendency to show energy drifts with longer time step, maybe more than 5 femtoseconds, and need much more storage space. And this algorithm is further advanced to some of the gear algorithm for higher accuracy by taking higher order derivatives of atom position. So these are the three main algorithms which are used. But apart from this, also some of the new algorithms are also coming up. Okay. Now knowing all this main principle behind this molecular dynamics, now get to the actual simulation for the how the actual simulation of molecular dynamics is done. Okay. So essentially, you start with some of the initial position, initial velocity and structure. Then we go for the initialization. Okay, and also before we run it, also we need to consider some of the pre-setup. Okay, we need to use that the periodic boundary condition. We also need for a long range force calculation. Also, we cannot use, let's say, force on a particular atom may be dependent on a large number, but we cannot consider all those atoms. So we need to use some of the cutoff. Okay, and also we need to use some of the nearest neighbor, number of nearest neighbor, distance. Also we need to consider the time step. Okay, generally in most of the cases it is in the range of femtosecond. At the same time, also we need to check for the time duration for this the run, and some part of the initial run are called the equilibration run, and then we got the exact the main MD run. Main MD run, from the main MD run only we calculate the different properties. Okay. So these are the initialization and some of the precondition. Then go for the numerical solution of the numerical. Also, you need to see what are the different external condition or ensemble, whether it's at constant temperature, constant pressure, or whether it is at constant energy and all. Okay, and for that essentially we need to use some of the ensembles. Okay. So then comes the integration or equilibration step, where we use essentially we go for the force calculation. From the force calculation we get the acceleration, and also we use those different algorithms. Okay. Then we get the data, and with this data, from the data we can get the different static and dynamic. So this is essentially the flowchart for molecular dynamics simulation. Okay. Or now, as I have mentioned, this kind of the parametric or analytical form of the parameter, the potential parameter, but the potential parameter also can be generated from the ab initio calculation. So those kind of these are called the ab initio molecular dynamics. In that case, you don't have to use any external potential, this interatomic potential, but we can use the potential which is generated by the DFT methods, and those potential can be used to calculate the force, and all using this different algorithm also we can do this the molecular dynamics. So molecular dynamics are two types, essentially classical molecular dynamics, where we externally supplied the potential, or the molecular dynamics also can be ab initio potential dynamics. In that case, we don't have to supply external potential, but the potential generally we get the potential from the ab initio run directly. Okay. So today we are considering mostly the classical molecular dynamics. So these are the steps for the classical molecular dynamics. So first we calculate the force on all atoms from the given potential, calculate the acceleration A on all atoms from the force. Okay, and then using this acceleration so if you know the force, from there you get the acceleration, and you can use the acceleration to get the velocity and also to get the new position. So we can calculate the Ri, Vi and Ai. So Ai may be, let's say, a kind of denotes the position of a particular atom I. Okay. At later time, T plus delta T numerically using these finite difference methods, and using the calculated data as input for the next round, repeat the process until equilibrium is. Equilibrium means when the atoms don't subject to much force. Okay, essentially we consider a kind of a cutoff to the force. If we say that the force is less than that cutoff force, we consider that this is under equilibrium. Okay. So when the equilibrium is reached and stable trajectories of the atoms, we get it, and from there we calculate the other properties. Okay. The three most popular numerical integration algorithm we have already discussed are the Valet algorithm, velocity Valet algorithm, and also Predictor-Corrector algorithm. But nowadays different new methods are also coming, like gear method and all. Okay, so some of the pre-setups before we do for this, because we need to how many number of atoms we need to take in order to represent the true material system. Okay, so for that we need to go for the some of the MD pre-setup. One of them is called the periodic boundary condition. Okay, so if you consider a simulation, you take a box and consisting of, let's say, 1000 atom, and let's say they are in a FCC lattice. So what we can see that we will say that half of the atom, almost 500 atom, will be on the surface. Okay, if it's on the surface, then its coordinated is not same as in the bulk. So essentially we are not representing the bulk materials. If we just take a box and all. Okay, so how to be considered as a bulk, atoms of roughly 1 mole you need to. So in order to consider a bulk, you need to have a large number of atoms. Okay, so that you can neglect somehow, or you can that means the number of atoms inside is more than the number of atoms in the surface. Okay, so in that case you may need maybe 1 Avogadro number of atoms. Okay, which is kind of impossible to deal with. Okay, so how to tackle this problem? Okay, so that in order to tackle this problem, we use called the periodic boundary condition. take care for this problem by surrounding the box with an infinite number of its image boxes all around. So you consider a box, and then in all the faces, let's say if you have a cube, so all these 6 faces, even on the corner side also, it will be all surrounded by some of the imaginary box we consider, infinite number of imaginary box. Okay, then but the actual simulation takes place only in the atom inside the primary box at the center, and all the image boxes just copy the primary boxes. Okay, for examples, so essentially it looks something like this. Let's say you are dealing with let's say this central box, within using and surrounding this central box you have got an infinite number of similar type of box which are imaginary. Okay, so you are running this, but if a particle moves from here to here, okay, so essentially what essentially does that another particle also move from let's say from the below imaginary below boxes to the center. So that kind of convention we use in periodic boundary condition. So actual simulation takes place only for the atom inside the primary box at the center, and all image boxes just copy the primary box. For example, if an atom K in figures move out of the primary box to the upper image box, its image atom in the bottom image box moves in to replace it and keep the number of atom constant in the primary box, as I have shown. Okay, note that the forces between an atom and its periodic image can cancel each other, and simple coordinate transformation can update the position of atoms in neighboring image boxes if necessary. Okay, the same trick can be applied not only to the bulk but also to the single atom and also cluster system by use of this. So not only the bulk, also we can represent the surface or interface by using the periodic boundary condition like here. So this is the bulk. Okay, so all the atoms, so essentially we are considering this simple periodic PBC, periodic boundary condition. Okay, but if you have a surface, in the case of the surface, or essentially the surface is essentially you have got a gap. Okay, so what we can do that we can take the periodic boundary condition, the periodic boundary condition something like this. We take periodic box is something like this. Okay, similarly for the case of interface. Okay, let's say we can take these two different the one box one materials, another box another materials, and we can do this. Okay, so these are the different representation of PBC periodic boundary condition for or periodic box for bulk, surface and interface. Okay. So another preset of also now we got the problem sorted out by using periodic boundary condition to treat a bulk, mostly bulk and surface and all. Okay. Now how many, so in order to calculate the force on a particular atom, how many neighboring atoms we should consider? Okay, or how many the force contribution coming from the neighboring atom also you need to consider. So for that case essentially we go for the potential cutoff. Okay, the most time consuming part in a molecular dynamics is the computation of forces generated by the potential acting on the atom, essentially the negative differential of potential, the gradient, negative gradient of the potential. Normally a potential tail off at long distance, as you can see that, let's say this is the potential energy curve. So this as you go further, so essentially this you see that the potential energy it is going to 0. Okay, so no point of considering a larger interaction coming from the larger distance. Okay, so normally potential tail of a larger distance become negligible, and this allows us to disregard the force calculation where the interatomic distance are beyond a certain cutoff distance, which we call it the R cut. Okay, this R cut must be smaller than half of the primary box size. It should be, so this is a convention generally followed, it should be half of the primary box size. Okay, otherwise an atom may interact with an atom in the primary box and its image in the image box, which causes some unphysical double counting or double interaction. After the cutoff, the potential tail is normally tapered such that the tail vanishes at the R cut to prevent any sudden discontinuity on energy and force. Essentially what we are seeing that at R cut the energy is 0, potential energy is 0. Okay, but actually if you go little bit down, little bit shorter distance, so essentially this is the energy. So we make a kind of this tapered case. Okay, so in this case now the interatomic force depend only on nearby atoms, and overall computation loads scale down to the order of number of atoms. Okay, so there are different normal cutoffs. If you use linear potential, this cutoff generally 2.5 to 3.2 into sigma. Electric the effective atomic potential or atomic methods essentially is around 5 angstrom and transfer potential around 3 to 5 angstrom. These are the cutoffs. Okay. Also, we need to use the minimum energy criteria. So essentially, let's say, so this will be cutoff. Let's say this R cut. So this black sphere will be of a sphere of radius R cut. Okay. And this, and also first we are considering a periodic boundary condition, then also one atom we are considering whatever the atoms are there within this sphere only we consider, not the other one. Okay. But at the same time also we need to look for the minimum image criteria also. Okay. So during an MD run, the force calculation of an atoms are carried out until all the atoms within this potential cutoff. Okay. The atom I has a, let's say this atom I has a neighboring atom, let's say K. Okay. But this K within the main calculation box, it is outside the R cutoff. But if you take the image of this K here, so you can say that this is within the R cutoff. Okay. So only R cutoff is not sufficient, because if you, when you use the periodic boundary condition, what you need to have is called the nearing neighbor list. That also we need to consider, because one atom in its main box may be outside the R cutoff, but that the similar atom in the image on the nearby image boxes may be within the R cutoff. Okay. So that also you need to consider. So that's what it is mentioned. Okay. The atom I has a neighboring atom K in the primary box and many K dashed. Okay, like here, maybe somewhere here. Okay. Among the atom, only the atom K dash is in the image box at the left in the closest atom, closest one to atom I, and will be considered for force calculation, which is called the minimum image. So essentially also you need to consider the minimum image criteria. Thus, two atoms in the image box at the left are included for force calculation instead of their real counterparts. Okay. So when a potential reaches long range, as in the case of the Coulombic interaction generated by charge or polarized atoms, so this criteria is not applicable. Okay. Then also we need to look for the neighbor list. So during an MD run, each atom moves various distances, and it is obvious that force calculation for the atoms that moves trivial distances are just meaningless. Okay. So Verlet proposed a scheme to avoid this unnecessary calculation by listing nearby pairs of atoms and checking their travel distance. And in this technique, a larger circle, sphere in 3D of radius R list than the potential cutoff is drawn around this each atom. Essentially, this is the R list. Okay. This one, this gray part. Okay. And in most MD code, R list is set around 10% more than the R cut as the default value, and a list is made of all the neighbors of each atoms within the circles. So this will just avoid this kind of, you should not miss this image one. Okay. After some fixed number of time step for updates or n up, force calculation are carried out only for the atoms move more than the delta R by 2. What is delta? Delta R is nothing but this one, this distance, this R list minus R cut. Okay. So that is the delta R. Okay. And it is prearranged that the list is updated at every number of this update steps before any unlisted atoms enter into the circle, as typically maybe in the 10 to 50 molecular dynamic steps. Okay. So R list minus R cut essentially more than the number of this update number into velocity into delta t. Okay. Then time step. What's the time step you should follow? Since atoms in a solid lattice vibrates in the range of 10 to the power minus 14 second, we have to use minimum time interval in the range of 10 to the power minus 15, because the atomic vibration is in the range of 10 to the power minus 14. So in order to realistically model the materials, the time step has to be less than 10 to the power 14. So that's why generally we use 10 to the power minus 15 second or femtosecond. And this small time span delta t is assumed that the velocity, acceleration and force of each atoms are constant in this time step, so that we can perform the simple algebraic calculation. So within this time step there is no change in the acceleration, velocity and all. Okay. To speed up the simulation time steps should be increased as much as possible. If you increase the time steps, so that to get certain time molecular dynamic calculation, the number of steps should be less. Okay. So speed up can be possible by increasing the time step, but if you increase time step, essential physics we are also neglect. Okay. So a practical rule is that atoms should not travel more than 1/30 of the nearest neighbor distance in this time step. Okay, which leads to a typical time step from 0.1 to several femtoseconds. Okay, computational load and accuracy with respect to time step is a trade-off problem. Okay, so a smaller time step increase computational load and normally improve accuracy, and a larger time step occur the opposite way. If the total energy becomes unstable, drift or fluctuate too much, it is an indication of too large a time step that overshoot the equilibrium position. Okay, so for atoms that move relatively fast due to high temperature or lighter mass or steep potential curve, a shorter time step is recommended. Okay, so time step is also very important. Generally, we use 0.1 to 1 femtosecond. Okay, in molecular dynamics. So what should be the total time? So a typical molecular dynamics run may take around 10 to the power 3 to 10 to the power 6 time steps. That costs maybe million time step you need to go for. Two total simulation types. So essentially 10 to the power minus 15 into 10 to the power minus 6. So essentially we get around 10 to the power minus 9 second or some of the nanosecond run. So that means you are capturing the physics for around 10 to the power minus 9 second or nanosecond. Okay, normally this is sufficient to see usual static and dynamic properties in materials. Okay, running an MD too long may cause error accumulation and inefficiency of data production. Total simulation time, however, should be longer than the full relaxation time of the system to have reliable data production. Okay, so first initial position or initial velocity are just not up to the mark or not at accurate relative to the overall atmosphere or overall imposing external condition. Okay, so first thing that we need to go for equilibration or relaxation. Okay, so that it gives a kind of a relaxed structure, and then we actually done. Okay, so especially for phenomena such as phase transition, vapor deposition, crystal growth, and annealing of irradiation damages, the equilibration takes place very slowly, and it is necessary to ensure that the total simulation time was long enough. MD runs start to bring the unrelaxed initial system to the equilibrium, so that minimal potential energy where the net force on each atom becomes 0 under the given condition, and so that erasing the memory of the initial. So first thing that we erase the initial memory, initial configuration. So for that, essentially go for first the equilibration step or relaxation step, and then the actual the MD run. From there we calculate the properties. Okay. So now in order to take care of the external condition, we need to use the different kind of the ensemble. Okay. So in a simulation box of an MD run, each atom moves and behave differently, and a new microstate of the system is generated in every time step. So after a proper equilibration and simulation, it becomes an ensemble. What is ensemble? Is nothing but a collection of possible configuration, and yet has the same macroscopic or thermodynamics properties. Okay, so in experiment we impose external constant on ensemble to have the particular properties, especially thermodynamic properties such as entropy, Helmholtz free energy, Gibbs free energy, and chemical potential can be derived from data obtained from this prearranged ensemble. So in order to get a different particular property, we need to use their corresponding ensemble. Okay, so there are mainly 4 types of ensembles are there, which is called microcanonical, called NVE, where N is the number of atoms, V is the volume, E the energy is fixed. We are not changing it. Okay, and what kind of system it is? It's an isolated system, which is very common in molecular dynamics, and in this case we can get the entropy value from the partition function if you do the ensemble. Okay, canonical NVT, where energy is not conserved, temperature is conserved, energy can vary, and this is the most common in Monte Carlo and common in molecular dynamics. We can get the Helmholtz free energy if we run the canonical. Isobaric and isothermal, where the pressure and temperature are fixed, and also of course the number of atoms is fixed, and here in this case we can get the Gibbs free energy. Grand canonical, in this case the number of atoms may change, and we can get the then we can get the chemical potential value. Okay, so these are the different ensemble we need to use to get particular type of properties. Okay, and accordingly also algorithm also should be there to for a microcanonical system to conserve the energy. For a canonical system, it should be some kind of treatment needs to be there so that the system is at constant temperature, because let us say if you temperature is related to velocity, and velocity is also vice versa related to temperature. At the same time also velocity is related to pressure also, but pressure we can also change it if we change the overall volume also. So there we need to use different algorithm in order to control the temperature. So this controlling are called the thermostat or biostat. Okay. So these are the different ensemble what we have just discussed: microcanonical, canonical, isothermal, isobaric, and grand canonical. So except microcanonical, essentially what you need to have there, you need to have a external bath to conserve the temperature or to supply of the sufficient particles. Okay. So these are the control methods, how to control the temperature and pressure for canonical and isobaric and isothermal process. So in an actual experiment, a MD run of NV ensemble often requires a constant temperature, and it can be achieved by rescaling the velocities following the basic knowledge of kinetic energy. Okay. So average kinetic energy, we know that is related to the velocity or the temperature. Okay. And from the average velocity, and the temperature also can be directly related to the average velocity like this. The average velocity, this is kind of an ensemble average velocity, is proportional to the square root of temperature in absolute scale. Okay. So it is possible to increase or decrease the temperature from T to T dash by multiplying each velocity component. So from these two we can easily get it. Okay. Using this equation, the velocities of all atoms are gradually increased to the desired value in predetermined iteration steps. To maintain constant pressure, extended ensemble like Boron states is adopted, and volume of the system is generally allowed to change. So these are the different the thermostat and biostat used: Nose-Hoover, Berenstein, CSVR, Langevin, and direct descaling, dissipative particle dynamics are popular thermostat and biostat. So these are mainly Nose-Hoover and Berenstein are used for the biostats, and others also used for both the mostly for including Nose-Hoover and Berenstein are used for the thermostat. Okay. So initialization, that means you need to start from initial structure. At the same time also better to give some of the initial velocity also. Okay. So to start an MD run, several initial inputs should be prepared to maintain meaningless to minimize the meaningless data and to have the reliable results. Okay. So number of atoms also, it should be system size, the number of atoms in the primary box should be as small as possible, but at the same time, as long as it can represent the real system properly. For reliable data production, more than 100 atoms are normally required. Okay. So initial position and velocity, to solve the Newton's equation of motion, the initial position and the velocity have to be provided. The initial position of the atoms are normally specified according to the known lattice position. The initial velocity of atom are generally normally and randomly chosen from a Maxwell-Boltzmann or Gaussian distribution at a given temperature. For example, the probability that an atom has a velocity v at an absolute temperature T is given by this expression. Okay, so this is the probability that a particular have the velocity v given by m by 2 pi kVt, where kV is the Boltzmann constant to the power of half exponential minus mv square by 2 kVt. Okay. The direction of velocities are also chosen randomly to make the total linear momentum become 0. Okay. So now some of the energy minimization steps. Essentially, we use the numerical method like steepest descent method or conjugate gradient method. Okay. In the steepest descent method, the method starts by calculating the potential energy for the initial configuration of atoms, and the atoms move towards the lower potential energy until the search line meets the potential gradient perpendicularly. So check whether the potential gradient is meeting the next layer as a perpendicular position. Okay. Since any further advance leads only to higher potential energy, the next search start at that point along the direction of the steepest descent as shown here. Okay. The process repeats iteratively until the minimum minimum energy configuration of the atoms is found. Thus, the search path is in zigzag fashion with many orthogonal steps that make this method relatively slow. Okay. And conjugate method, this method start by searching along the direction of the steepest descent and stop at a local minimum and then figure out a new search direction based on both the new energy gradients, negative value of the force between the atoms, and also the previous. Essentially, it's look for the change in the gradient. Thus, as shown, the search path is rather straightforward with fewer steps that makes this method relatively faster than the earlier methods. An extended scheme is the quasi-Newton method that considers an additional information like second differential of the potential energy. Now, problem with this energy minimization is that instead of going to a global minima, it can also reach to the local minima. That means this it can have different localized minima, okay, and then the the energy of the localized minima may be more than the global minima. So, you may end up in the local case. Okay, that means not at the exact very stable position, you are reaching to some kind of the transition state. Okay. So, in order to avoid that, people use different other algorithms. It's called the simulated annealing and all. Okay. So, after doing all this calculation, we get the data, and this data can be used up to get the properties. What are the properties we can get? We can get the total energy of the system given by the summation of the kinetic energy and potential energy. At the same time, also we get the temperature, and we can get the temperature and energy function, which, and from there, from the change in the slope, we can get the different transition also. Okay. We can get the structural property, like we can get the equilibrium lattice constant, cohesive energy, we can get the bulk modulus, because we are getting the position, velocity and acceleration, at the same time also energy in each step. Maybe we are not capturing all this data for each step. Maybe we can take the average between some of the combined steps. Okay. And that we can use for getting these different properties. Okay. We can also get the thermal expansion coefficient, we can get the radial distribution function. So, this radial distribution function, one of the major output from the molecular dynamics are the radial distribution, which give the structural characteristics of the materials. Okay. So, in the radial distribution, as in the X-ray diffraction, the radial distribution function here can show how atoms are distributed around a certain atom. So, it is obtained by summing the number of atoms found at a given distance in all directions from a particular atom. So, it just go on increasing the number, the radius from a particular atom, and count how many number of atoms are there on each incremental this spherical sphere, if we just increase the radius. Okay. So, that gives you the radial distribution function, and from the radial distribution function we can get what the number of nearest neighbor and also the nearest neighbor distance. From the nearest neighbor distance we can say that what kind of bonding it can have and all. Okay. At the same time also, with temperature and pressure, how this nearest neighbor, how this radial distribution function or RDF changes. From there you can say that whether any phase change is occurring or not. Okay, like here, let's say this is the radial distribution functions. So, let's say you are going increasing for a particular, you take a particular atom, okay, and then in C, as you go up away from that atom, what are the different types, what are the number of atoms are there. Okay. So, in this case, it's when you come around, let's say 2.2 angstrom. So, you say that number of atoms are now count number increased to 5. So, you can say that this is the first coordination. Okay. This is the first, the second, or you can say the first nearest neighbor, and this is first neighbor, and this is the second neighbor. Okay. Now, if it's crystalline, this will be fixed, but if it's a kind of a amorphous, you will say that you get a kind of this sprayed one, or if you get a liquid, also you will get the sprayed is more. So, from this radial distribution function, we can say about the structure of the material. Okay. Coordination number also, if you know the RDF. Okay. Also, apart from the RDF, also we can get the mean square displacement, which can be used to get the diffusion coefficient and all. Okay. What is mean square displacement? So, the vector distance that an atom travel may be close to 0. Let's say it is going left, right, up and down, but at the same at a time interval, it may so if you take the average of it may become 0. That means it will say that the average it is not moving on an average basis. But at the same time, but molecular dynamics, all the atoms are moving. Okay. So, So we get the for that essentially what we can make it, we can make all the displacement, all these change in the position as a positive, and for that what we take that is the modulus. Okay. So the vector distance that a atom travels may be close to 0, since that atom might take either a forward direction or backward direction, or upward direction, downward direction. Okay. Nevertheless, if we take the square of this displacement, we will have a non-zero positive number, that is called the mean square displacement, or MSD, over some time interval t. And by arranging the overall time, the MSD will have a linear dependency, something like this. Okay, we take the square of it. Certain change in the MSD with time are indicative of the melting, solidification, phase transition, etc. In the case of solid, the MSD becomes a finite value, and for a liquid, however, atoms will move indefinitely, and the MSD continues to increase linearly with time. The self-diffusion coefficient in liquids D can be derived from the slope of the MSD, the time relationship, like this way. What we get the self-diffusion coefficient 1/6 of the MSD divided by the time. Okay. So these are the common molecular dynamics simulation programs like GROMACS, LAMMPS, NAMD, OpenMM, CHARM, AMBER and all, which mostly use the classical type. That means where external the parametric based analytical the empirical polynomials, or maybe some functions are used to get the potential to give the potential parameter. Okay. Or molecular dynamics can be of also the where you don't have to supply, which is called the ab initio molecular dynamics, or AMD. Some of the program for AMD are CP2K, Quantum Espresso, VSP, VASP, Gaussian, NWK, Siesta and all. Okay. So you may search on this different program, their websites. Most of them are free. Okay. They have also well maintained user manuals and all. Okay. So in order to run it, essentially we need to go through their website, download it, install it. At the same time also need to use some of the examples and also go through the manuals and all. Okay. So whether the runs are kind of the good or bad, so you need to validate it. So the validation, one validation is that conservation of energy. Okay. So that is the one way. Another is that whether confirmation of the global minimum. Okay. And in order to avoid the local minimum, what we can use? We can use the simulated annealing. So the simulated annealing, what it does, we equilibrate at higher temperature and slowly cool down to 0 Kelvin. And the system has enough chances to look down and identify many different minima on the potential surface and to move over local barriers to arrive at the global minimum. Okay. Another validation is the time average under the ergodic hypothesis. What essentially says that time and ensemble or statistical average are interchangeable. So in that case only we can use the statistical method to get the average property. Okay. So that is essentially the ergodic. You need to conform to the ergodic hypothesis. Okay. And the last one is that you also need to see the errors, whether the errors are building up or it is diverging and all. Okay. So another two types of errors are there in numerical solution. One is the truncation error, which depends upon the method itself. So you need to change the different methods to minimize the error, or round off error. Okay. Round off error nowadays is not much of concern, because we are using high precision the decomposition machine and all. Okay. So that's give the overall view of the principle behind the molecular dynamics simulation. There are different flavors of these. Nowadays, not only the atoms as a minimum basic unit, people are using the number of a cluster of atom as a unit, which is called the coarse grained methods. That is also there. And there are these molecular dynamics methods not only are used for the materials design or materials property calculation. These are also used for in the biomolecules, industry, medicine industry, like in the case of the drug design and all. Okay. Thank you.